Is the video visible?
Yes.
Yes.
Yes,
Yes,
sir.
okay. That's good. That's good. So I think we can proceed now.
Yes,
Okay.
sir.
Yeah. So all of you, please put off your mics so that you can hear me. Now, basically, we were trying to see what an hydrogen atom is, and at the outset, we discussed that the classical theories are not able to actually tell us all about the hydrogen atom. And so we have to shift to something called as a quantum theory. And when we are doing quantum theory, you will find Schrodinger's equation comes to our help. So in Schrodinger's equation of hydrogen atom, we are going to study the quantum numbers. That is how, after solving the Schrodinger's equation, we are getting total quantum number, orbital quantum number, and magnetic quantum number. Of course, to get these numbers, one has to use the method called as separation of variables. Now, if you see, look at the Schrodinger's equation, it plays a role of Newton's laws and conservation of energy in classical mechanics. That is, it deals with so-called force and energy, and it predicts the behavior of a dynamic system. It is a wave equation essentially, and in terms of wave function, which predicts analytically and precisely the probability of events or outcome. The outcome is not strictly determined, of course, in quantum mechanics because we talk of probability, but a large number of events Schrodinger's equation can predict by the way of distribution of results. Now in SYBSC, you had studied a lot of quantum theory, I know, and some of you might got confused because it has a lot of equations and it is not the same as classical theory we are studying. But here today, I am going to show you a very simple equation of, you can see that kinetic energy and potential energy is equal to total energy. All right. And then kinetic energy we always write as half mv square and potential energy as half kx square, which is equal to capital E. Also, we know that F is equal to ma, and then it can be, in terms of restoring force, can be written as minus kx. Now, if you look at the LHS, then we know that momentum P is nothing but mv. So if you take p square by 2m, it is half mv square. Let us keep half k square as it is. Now, when we are using quantum theory instead of classical, okay, we have to change the physical variables like momentum or let us say, okay, into the operator. Okay, so the momentum operator is h cross upon I deba by deba x as it is shown in the screen. But we want p square. So if you take p square, it will be minus h cross square upon 2m deba square by deba x square, where we have got rid of that I and then it brings minus sign into the Hamiltonian. Now this operator, the whole thing left hand side now, in terms of operator, can be written as minus h cross square upon 2m deba by deba x square plus half k square. Now this is called as Hamiltonian operator H. Okay, so we can now say the equation becomes H psi is equal to E psi by adding psi on both the sides. The left hand side is H Hamiltonian operator and the right hand side is energy eigenvalue E. Okay, so what we have seen in this is that the kinetic and potential energies are transformed. Okay, the left hand side has been transformed into Hamiltonian, which acts upon a wave function psi to give us a evolution of wave function in space and time, that is the energy eigenvalues. The Schrodinger's equation gives quantized energies of system and it gives the form of wave function so that all the properties, almost all the properties of the system may be calculated. So let us go back slightly to the above equation. And then now in terms of quantum mechanics, we can write it as, instead of H, now just remember H psi is equal to E psi. Very easy to remember. Okay. But remember, this is a quantum equation. Okay, so h will be replaced by minus h cross square by 2m debba by debba square plus half kx square psi equal to E psi. Okay, now let us get rid of this h cross square by 2m. Okay, by multiplying the equation by h square by 2m throughout. Okay, then what is left with is debba by debba square debba x square psi plus, now this half kx square is actually v, the potential energy v. So you can take out common and write del square psi. Okay, okay, plus h cross square by 2m into bracket v minus E psi equal to 0. So that becomes our Schrodinger's equation. I will quickly go on to it and we will see what it is, and then I'll come back again. You can see here, just a minute. Yes, if you look at the first equation here, okay, can everybody see this?
Yes, sir.
Yes,
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 sir.
yes. So see this equation,
Yes,
which
sir.
I'm showing you here. It showed del square psi plus 2m by h cross square into E minus V psi, VR psi of course, is equal to 0. So this equation we are now considering as Schrodinger's equation. Okay, so whenever we talk of Schrodinger's equation, I will refer to this equation now. But this has come from which? H psi is equal to E psi. So very easy to come to this point. Okay. Now let us go back and let me tell you what is happening. Okay. So we were here, and next we go to how we go about in Schrodinger's equation for hydrogen atom. Now, as I told you that there will be a lot of mathematics. So at times you may feel that whether we are sitting in a maths class or a physics class, but for time being you have to bear up with me. Okay, now we know that hydrogen atom is the simplest atom, consists of one proton and one electron, okay, which are bound together, let us say, by electrostatic potential between them. And then the potential energy we write as V is equal to minus E square by 4 pi epsilon naught. This is very simple. Okay, which is the attractive potential we say between a positron, that is an electron and a positive charge, and separated by distance r. So this is a proton exactly, and this is an electron in case of hydrogen atom. So let us go that if you look at that equation, then you see that V is function of r only. Okay, that is the radius vector only. So the potential looks very simple because we have been using this equation, but the potential is a function of r and it is not function of x, y or z. So these are the Cartesian coordinates. If we want to write r in terms of x, y and z, then it can be written as x square plus y square plus r square is 1. So now if you want r from this, of course this is the equation, r is equal to under root of x square plus y square plus z square. Okay, but when we are using this approach, okay, you will find that it takes a lot of time and energy to solve these square roots and come to some conclusion. So in quantum mechanics, it is always guided by something called as symmetry. Okay, symmetry of the whole hydrogen atom, which is actually a symmetric hydrogen atom, you can say. And then by every means we are asked to use a spherically symmetric potential that is called as spherical polar coordinates. So instead of using Cartesian coordinates, we will use spherical polar coordinates, and we were talking about this in my previous lectures. Now, if you go to this, then you will see that we essentially talk of r, theta and phi. Now this is the diagram which is going to give you the change between the Cartesian and spherical polar coordinates. Okay, so these are our regular coordinates x, y and z we use in the lab, mostly x and y, not z, because it goes into the book or comes out of the book. All right, so you can see that if you consider that hydrogen atom, the proton is at the center and electron is here, okay, at point P, then the distance between these two, okay, here this distance is small r, okay, one of our coordinate, okay, spherical polar coordinates कितने हैं? 3 हैं. It is r, theta and phi. R is this distance between proton and electron. Okay, theta is the angle made by the radius vector with z axis. You can see here z axis. Okay, and it can be expressed like this in terms of cosine. Okay, so cosine, if you take cos theta, okay, that will be the adjacent upon the whole hypotenuse here, and we know r is nothing but under root of x square plus y square plus z square. So we get theta in this form. Similarly, this phi is nothing but you drop, okay, a projection here from the, let us say, electron onto the x and y axis, common of x and y axis here. Okay, projection vector on x and y, and now this connection, okay, the projection, the angle between projection of radius vector on x and y and positive x axis now gives you what is called as phi. Now, if you want to write phi, it is always in terms of tan. So if you say tan phi, that will be opposite side upon hypotenuse. So if you take that way, then it can be written as phi is equal to tan inverse of y by x. Okay, so now instead of x, y, and z, we are talking of some coordinates r, theta, and phi. So now we write x, y, and z in terms of r, theta, and phi. Okay, okay, using these equations. Okay, so we get x is equal to r sin theta cos phi, y is equal to. Now these equations how we have got will be more clear when I will go to the next part of next slide of my presentation, wherein it is clearly shown that how we are going to arrive at this part. But otherwise, if you want, you can see inverse cos theta is z upon r. Okay, or sin theta is y upon r sin phi, or in case of cos phi is x upon r sin phi, that you can see there. Now again I come back to the Schrodinger equation. Do you remember what I showed you? Del square plus 2m by h cross square e minus v psi equal to 0. Do you remember?
Yes.
Yes,
Yes,
sir.
sir.
Yes.
Yes, sir.
Yes. So this del square, see now this del square is written as d by dx square, d by dy square, d by dz square in all the three. And then you are adding psi to it. So this becomes a del operator. And then we have our own equation plus 2m by h cross square e minus v psi equal. So this is a Schrodinger's equation of form del square psi plus 2m by h cross square into bracket e minus v psi equal to 0. All right. Let us go a step forward. Now for your something to make it easy, I have given some 1 or 2 slides where actually you can go to what I'm trying to tell you. Okay, in this slide you will be able to know, see the direct Schrodinger's equation is given here, the top equation 1. Then x, y, and z coordinates are written in terms of r, theta, phi, and then using this equation we know x square y square plus z square is r square, and r is of course under root of this, tan phi is y by x and tan theta is, so it is shown here. And then you can solve the whole thing. You can see here mathematical expressions are given. Okay, these mathematical expressions are actually not needed when we write the derivation. Okay, because I am going to come from here, this equation del square psi plus this into directly here at this point. So I will say that the Schrodinger's equation del square psi 2m by h cross e minus v, this equation can be written in terms of spherical polar coordinates. This 1 by r square divided by deb r and this whole thing. ये बड़ा इक्वेशन जो दिख रहा है एकदम नीचे, ये स्लाइड के एकदम नीचे एक बड़ा इक्वेशन दिख रहा है. ठीक है, जिसका जो लास्ट टर्म है देखो 2m by h cross square e minus v r psi equal to 0 वो सेम है पहले से, लेकिन डेल स्क्वायर जो है डेल स्क्वायर psi उसके लिए ये इतना बड़ा इक्वेशन है. तो ये इक्वेशन पे आने के लिए तुम ये मैथमेटिक्स देख सकते हो, तो बहुत डिटेल दिया हुआ है. ठीक है, इसके लिए इसको मैंने थोड़ा अलग स्लाइड में डाला. इज इट क्लियर नाउ?
Yes, sir.
Okay, so we
Yes,
are on
sir.
this equation.
Yes.
We are on this
Yes,
equation. This is called as Schrodinger's equation. And then this slide, this is for you, okay, as a homework. This is for you as a homework. And now I directly come to the spherical polar coordinates. So that Schrodinger equation, in terms of spherical polar coordinates, it is written like this. You can see here, okay, in which the third term you can recognize. Sorry, not the third, first, second, third, fourth term. You can recognize because it is same as the previous one, same as this one. Okay, here. All right. Other three terms you will find first term is in term of r, small r. You can see 1 by r square divided by deb r square d psi by d. So this is a term in r, small r. While the second term is in term of theta. third term is term of phi and of course psi and phi, but phi mostly or theta. Okay, now what you have to do is with this Schrodinger equation you have got here, which is in spherical polar coordinates, we are going to play maths. Okay, and after playing maths, you will see that we can arrive at the three quantum numbers. What are they? N, L, and Ml. Let us see how. Okay, now with this equation, we are going to say multiply both sides by r square sin square theta. So all these terms are multiplied by this r square sin square theta, and you can have a equation like this. Okay, okay. Now this equation gives you wave function, okay, of electron in hydrogen atom. This equation, what we have got here, if we solve, okay, of course by using something called as separation of variables, then you know everything about hydrogen atom. Okay, so when we solved Schrodinger's equation in one dimension, we found one quantum number was necessary to describe our system. Okay, maybe that is n. For example, in Bohr's atom of an electron moves in orbit, we know electron moves in orbit, but we need only one parameter. Okay, that is r vector. But here in three dimensions, okay, we see that we need three quantum numbers to describe our electron, not a single, just a space quantum, but we need the whole thing. Okay, so Weiser at the end of this section, because this is a note taken from Weiser with, of course, you can see here, there's a notes plus modern physics Weiser as it is subscribed in your, prescribed in your syllabus. Okay. So another comment I would like to give here is we are really solving Schrodinger equation for electron in hydrogen atom. Okay, we talk of hydrogen atom because our solution will provide us with much what we need to know. That is, you will know everything about hydrogen atom. Okay, so let us jump to a mathematical term called as separation of variables. Okay, we will discuss this technique now. All right. Okay, so here are some things we like in decreasing order of liking. You can see we have linear algebraic equations, coupled algebraic equation, linear coupled differential equations. When we have an equation like the one above, or which involves all these things, if you look at the equation, Schrodinger equation we have written, it's a big equation, and now it is very difficult to remember. Okay, unless and until you put your lot of efforts into it. Now let us see how we can separate variables into this. Okay, there are three variables r, theta, and phi. So now we say psi, instead of function of x, y, and z as we usually used to take, now we say it is a function of small r, small theta, and small phi, such that r is a function of r only, theta is a function of theta, and phi is a function. So you can write it r, theta, phi. So this is our assumption. Okay, that psi might be. Why are we doing this? Because we want the quantum numbers, one quantum number from r, one from this theta, and one from this phi. Okay, now let us go ahead. And now if I take d psi by dr, okay, if I differentiate psi with respect to small r, then what I will get? The other two terms are constant. Theta and phi will be constant, and we have dr by dr on this side, deb r by deb r. Okay, okay, and in terms of actual, you can say. Similarly, if I take the differentiation of psi with respect to theta, then the other two, leaving this theta, r and phi will remain constant, and we have got this term. Similarly, you will have third term where we say d square psi by d phi square, the third term. Okay, where the partial derivatives become full derivatives because r, theta, and phi depend on r, theta, and phi, in the sense r depends on r, let us say, theta depends on theta, and phi depends, because they are independent variables. Okay, and so we can change the partial derivatives here, deba into dt. Okay, now we have got to separate the variables. Let us say psi is r, theta, phi into Schrodinger's equation and divide by r, theta, phi. Now what we are doing, the equation we have taken here, just a minute. Here the equation we have taken this one. We are going to divide it by r, theta and phi. Okay, because now we define it like this. Okay, so if you divide it by r, theta and phi, now you start looking. See here, you have got capital phi, theta. Sorry, you got capital phi, you got capital R, because we have divided the equation by r, theta and phi. Okay, note that we have separated out phi variable. Okay, now if you see the term 1 upon phi d square phi by this term, just this term, what it contains? All phi's, either capital or small. All right.
Yes, sir.
Yes.
Yes, sir.
So
Yes.
yeah. So we can say that this term, this third term, first, second, third term is a function of phi only. Okay, and let us put it on the right hand side of the equation. That is, take this term from here and take it here in place of 0, right hand side. Okay, this gives us an equation of this form. Okay, now since this is a positive here, go there, become negative. Other terms remaining the same. Okay, well, now what do you note from this equation? Let me again show you the equation. See here, if you see the first term, okay, you can see only r's there, right? Am I right?
Yes.
Yes,
Yes,
sir.
sir. Only r's can be seen.
Yes.
Okay, the second one only theta can be seen. Okay, and the third one is phi can be seen. All right, and now what we have done, now I'll go further. This is function of r, this function of theta. Let us not talk about this right now, but this is a function of phi. Okay, here notice the form of equation. If I have f, r and theta in this form, g psi, okay, where r and theta are the two variables, okay, which are independent of course, but they are kept on left hand side and phi is kept on right hand side. Clear? So what we can say that f is function of r and theta only and g is function of phi only. Clear? Under these circumstances, if this thing happens, then we can equate the RHS with some constant. Okay, like f r theta, and if you take g psi as some constant, then it is a constant which is independent of r and theta. Okay, so now we can say the g psi I can equate to some constant by using this method, and then I go and I equate it with the constant ml square. Okay. Okay, so the minus that right hand side minus 1 by phi d square phi by d is equal to ml square. This is an assumption. Okay, now what is ml? We know it is nothing but the magnetic quantum number. Okay, so just remember first one. Then you have equated it, okay, to ml square. Okay, now LHS of Beiser equation must also be equal to ml square. Since right hand side you have equated this, you have equated to ml square. So the left hand side will also be equal to ml square. See, this whole thing will be equal to ml square. So since this is equal to ml square, this thing, this LHS will also be equal to ml square. Okay, so it will always be equal to. And now if you rearrange this and equal, if we set LHS equal to ml square, divide by sine square theta and rearrange, that again a small mathematic trick is played here. So we get this type of function. Okay, once again we have separated variables. You can see the LHS is function of r only. See, this whole thing is r. Can you see? Okay, see here it is r, small r, capital
Yes.
R. So now the LHS is function of r only. Well, RHS is function of theta only. Now if this thing happens, we can equally equate it to some constant, right? As I said. Okay, there also we played the same trick. Okay, now you can equate it to some constant, but now this time this constant is LL plus 1. Okay, so let us say that these two are equal to LL plus 1. Okay, what is small l? Orbital quantum number. Okay, this is how orbital quantum number arises. So now we have three equations. The first one, that is this one. Okay, where you can rearrange this equation, take ml square on this side and rearrange, and you come to this equation. That's the first differential equation. Okay, then also these two we have separated to LL plus 1. So you can rearrange them separately. This R this first term here, you can separately equate it to L plus 1. Similarly, this right hand side you can always equal to L plus 1, and then you get these equations. Okay, of course ML square is there and you have to rearrange and do it. Okay, so this is the second differential equation and third differential equation. So what we have got is these three equations. First equation has ML, the second equation has L. Okay, and we can show that in third equation we can bring in L. The reason is you look at this factor E. Okay, and we know this is the energy of the orbital, and it is always related to small m. Okay, so to come to this point, we had a very big differential equation. We have separated it into three smaller parts, okay, by using separation of variables. Now, each one of them is easy to handle, okay, because we have separated the variable phi, theta, and r. You can see here phi, here it is theta, and it is r. Okay, so we don't have to bother about the whole equation, but we will talk in terms of these equations one by one. So let us take the first equation. This is our first equation. Okay, it has come from this equation where you have taken ML on the left hand side and solved it. Okay, and you get this equation. Okay, so first equation. Now if you have to solve this equation, solution of this equation is in this form. Okay, where this you have to remember, of course, where A is normalization and it is done using the rules of sines and cosines. Okay, and then you can say that since any event happens at phi, it will repeat itself after theta plus 2 pi. Like we have a wave, so one full wave, we come to some point. Again, second wave, we come to the same point. So at phi and phi plus 2 pi, we will again come at the same point. In that way, you will find that ML will have values. This will happen only. ML will have values 0, plus minus 1, plus minus 2 there. So where this ML is called as magnetic quantum number. Then we go to the second equation. The second equation you will find has this term. Okay. Okay. And what is that term? Small l. Okay. Now this ML, when it goes from 0, plus minus, plus minus, you can see that it goes till plus minus L. Plus minus L. So it is plus minus L. So you have got orbital quantum number. And if you take the third equation, okay, we are not solving it, but if you take the third equation and if you solve it, for example, you will come to a value of En, okay, where you will get small l. Now this equation is familiar to you because you had been doing this in your Bohr's atom model in 12th standard. So there comes the principal quantum number. So we have got three numbers, okay, depending on the three equations. Okay, the first equation was on phi and we got ML. The second equation was on theta and we got L. Third equation was an R radius vector. Okay, that is a distance between the proton, center nucleus, and electron, and we have got principal quantum number. So what it tells us? Our result for principal quantum number, okay, N and dependence of electron energy, of course, turn out to be same as Bohr's model. That is, we are talking of this equation. Okay, it is same as Bohr's equation, right? Okay. So we know that if we use this, that electron energies of hydrogen atoms are quantized and they are negative numbers. Okay, just as we had before. There's nothing special because if you have positive energy, then actually hydrogen atom cannot form. You can read this, there is no problem. Okay, so we can express now that L is 0, 1, 2 till n minus 1. Okay, so we have got three numbers, ML, L, and N, right? So any wave function of an electron, Schrodinger equation for electron, can be written in terms of R, theta, and phi. Where if you take R, it is dependent on N and L, small n and small l. Phi, capital theta, dependent on L and ML, and capital phi dependent on ML only. Okay, so we know that phi is function of three variables R, theta, and phi with respective quantum numbers. Okay, so we come to this point, and then if you want to go through this slide and solve something, you can do that, but this will come only when you go to your MSc. okay, where actually you can take numbers n, l and ml and solve the equations to come to certain point. And then of course you have got five, you can plot them. Okay, plot them and see what happens to them. Okay, so I'm not going to go through this slide, and I would say thank you for this lecture. Now, before ending this lecture, let me tell you that what we have done today, okay, is a I will say running commentary on Schrodinger's equation. When you actually sit and solve it, okay, it might take some time, but what I have done is I have put it in form of question answer. Okay, that how we are going to actually write if a Schrodinger's equation is asked for, let us say, 10 or 12 marks. Okay, then actually how we are going to write the whole equation to come to quantum numbers. Okay, that is L, theta and phi. Uh, okay, so that slide I think I will share with you later. Okay, so that you can write that question in question answer form. Is it okay with you? Yeah, so I think let me go back to my screen. I think I'll be able to. Yeah. So here I can see everyone here. Okay. Anyway, I can see some of you here. So let me quickly ask Anjana what you have learned today.
सर श्रोडिंजर इक्वेशन उसको हम लोग ने आर थीटा और पाई के टर्म्स में हम लोग ने देखा, उसके डिफरेंशियल इक्वेशंस देखे.
Okay. So before I forget, I want some one of you to quickly take a प्रेजेंट ही ले सकती है अंजना, स्क्रीनशॉट ले सकता है कोई? हेलो
सर ले लिया मैंने.
हाँ, स्क्रीनशॉट ले लिया
सर मैंने हाँ ले लिया मैंने सर.
हाँ, किसी ने भी लेना फिर मेरे को भेजना उसको. तो मैं नहीं लेता हूँ क्योंकि आज मैं पीसी पे बैठा हूँ, जरा सीख रहा हूँ क्या है. ठीक है, अरफा कुछ बोलना चाहेगी?
नो सर.
आज हमने क्या देखा या क्या सीखा?
श्रोडिंगर इक्वेशन पढ़ा और उसको बोर्स एनर्जी से कैसे पूरा डिराइव करते वो देखा और बस डेरिवेशन था सर.
ओके, मतलब बहुत ज्यादा मैथमेटिकल था. वैदेही, यू वांट लाइक टू से समथिंग?
हो सर. सर क्वांटम मेकॅनिक्स आपल्याला स्क्रोडिंगर इक्वेशन फॉर हायड्रोजन ॲटम सॉल्व्ह करण्यासाठी म्हणजे ते पर्टिक्युलर इक्वेशन सॉल्व्ह करण्यासाठी कसं आपण वापरू शकतो आणि म्हणजे हे आपण बघितलं मोस्टली. आणि एक मॅथ्सचा उपयोग करून आपण क्वांटम नंबरच्या डेरिव्हेशन म्हणजे क्वांटम नंबर पर्यंत कसं पोहोचू शकतो. एक तो वे होता आपल्यासाठी की आपल्याला जे क्वांटम नंबर अशी माहिती होते 12वी पर्यंत की हो असे क्वांटम नंबर असतात, पण ऍक्च्युली ते डिराईव्ह कसे होतात, आपण तिथपर्यंत कसं पोहोचू शकतो हे त्या इक्वेशनने आपल्याला सांगितलं.
राइट. We also have, I think, Dhanashri Thakur with us. Okay, Rutika Jadhav.
Yes, sir.
Would you like to say something, Rutika?
नो सर, मतलब हम लोग ने सब स्क्रोडिंगर इक्वेशन और सेपरेशन ऑफ वेरिएबल्स और वो डेरिवेशन से कैसे निकालना है वही सब देखा.
हाँ, तो जो हमने 12th में पढ़ा था उससे ये काफी अलग लगा होगा तुमको. तो इसके अंदर जो तुम देखोगे कि जो मैथमेटिक्स आता है वो क्वांटम मैकेनिक्स से रिलेटेड है. ओके, तो तुम लोग को एसवाई में जो थोड़ा डिफिकल्ट लगा उसका रीजन यही था कि क्वांटम मैकेनिक्स पे जो है ना उधर प्रोबेबिलिटी यूज करते हैं और ऑपरेटर्स यूज करते हैं, डायरेक्टली फिजिकल पैरामीटर्स यूज नहीं करते. इसके लिए जो साई फंक्शन है इट इज ऑलवेज रिटन इन टर्म्स ऑफ ऑपरेटर्स एंड वी सॉल्व इट. बट देयर इज लॉट ऑफ मैथमेटिक्स इन्वॉल्व्ड एंड आई डोंट नो, while studying all that mathematics we actually forget hydrogen atom. So that is the most funniest part of what we do here, but still uh, we get a lot of information about the atom. Shreyas is there?
Yes sir.
Yes, would you like to say something?
हो सर, आपण ते श्रॉडिंजर इक्वेशन बघितलं for hydrogen atom in 3-dimensional and ते आपण XYZ coordinates न घेता R, theta आणि phi coordinates मध्ये त्याचे functions ते function आहे सायचं असं मानून आपण ते इक्वेशन सॉल्व्ह केलं पण मला जरा अजून 2-3 वेळा बघायला लागेल ते नीट समजलं.
Yes, you're right. You're right. Even I.
Overview समजलाय.
Yes, even I would say that. See, you have to go through this equation, and that is the reason why I am, going to give you the notes. Okay. So most important is those slides which I showed in between. Okay, I will just show you again because there you will have difficulty when we say del square. Okay, psi. Plus 2m by h into that e minus v psi equal to 0. From that, when you come to the actual spherical polar coordinates, it's a long equation. Some of you might have difficulties. Okay, so I think where comes to your help the two pictures which I have given you, small slides which I have given you, which shows the total derivation. Okay, even if you don't understand from that, again I am going to give you notes in form of question and answer, so it is more clear there. Is it clear?
Yes sir. सर यावरती ते सॉल्व पण करायचं नाही असं तुम्ही बोलले की मगाशी की त्याचे क्वांटम नंबरच्या व्हॅल्यू नाही काढायच्या तसं काहीतरी का फक्त डेरिव्हेशन आहे.
See. Whatever notes I will give you, no? That notes are sufficient. You will get an idea from those notes what is to be written. Okay. Sir. So right now, if you want, I can repeat this lecture also with that notes if you wish to.
Sir, थोडंसं हळूहळू.
Yeah, but what I feel, I'll tell you. What I feel is, I can do it again. I will do it again. But what I feel is you have to, yourself sit and do this. Okay, because it has a lot of maths can be done on board. Okay, on board we can write down, but then in practice like this, it is difficult. So you have to sit at home and write this equation. So when I will provide you with my notes, it will be very easy for you. Okay, that is what I feel. Shreya, would you like to say something?
Today we saw an overview of how Schrodinger equation is for a hydrogen atom in terms of spherical coordinates and how there are conditions for quantum numbers. It was an overview.
Anybody else? Ritik Pillai, would you like to say something? Ritik Pillai.
सर वही स्क्रॉडिंजर्स इक्वेशन के बारे में पढ़ा और फिर उसका थोड़ा मैथमेटिकल पार्ट में ज्यादा फोकस किया आज, डिफरेंशिएशन एंड ऑल.
वो मैथमेटिकल से ज्यादा मैं बोलूंगा कि अपना मैथमेटिकल ही था लेक्चर. लेक्चर ही मैथमेटिकल था. ठीक है. अभिषेक सिंह इज देयर.
Yes sir.
Would you like to say something?
No sir.
Harsh.
Yes sir.
Harsh, would you like to say something?
No sir.
Okay, so I think we will stop here for today. Okay, Shubham is there?
Yes sir, I am here.
Shubham काय बोलायचं बेटा?
नाही सर, सगळ्यांनी बोलून दिलं सर.
तर काय करा, हे जे तुम्ही परत जा, हे स्लाइड्स ना, माझा जो टीवायचा क्लास आहे ना, कुठला जुनावाला, त्याच्यावर मी हा व्हिडिओ अपलोड केलेला आहे, म्हणजे हा पॉवर पॉइंट अपलोड केलेला आहे. ठीक आहे, तर यू गो व्हेरी स्लोली थ्रू इट. आई होप ऑल ऑफ यू आर देयर, अदरवाइज आई विल डू इट ऑन द न्यू ग्रुप ऑल्सो. मैं न्यू ग्रुप पे भी उसको डाल देता हूँ. तो यू गो थ्रू दिस स्लाइड स्लोली. Okay, and try to see what you can. Then when I will give you notes, I will post you my notes also. So there it is in question answer form. So there you will easily understand it. Okay, what I feel that if it is done in one stroke, it is always better. Some of you might have felt sir एकदम fast जा रहे थे maths को लेके. तो उसका reason भी वो था कि अपन Schrodinger's equation को spherical polar coordinates में convert करके जब तक अपन quantum numbers में आते हैं तो पूरा पोर्शन कंप्लीट करना था एक लेक्चर. ठीक है, इसके लिए. ओके, ठीक है, तो आज के लिए यही रुक जाते हैं. ओके, सी यू ऑल लेटर.
बाय सर.
बाय सर.
बाय सर.
Bye.